From the World's Fair in 1964, where Disney first introduced animatronics, to the Jurassic Park movies and rides all over the world, dinosaurs have always played a huge part in animatronics history. So when I came across a technique to build really realistic reptile skin, I knew I had to make a dinosaur animatronic myself. But before we can ever get to making a skin, we need to build the mechanics that go on the inside. All mechanical design starts in CAD, and I actually did something here that you'd usually do in a more artistic 3D modeling environment like Blender. I downloaded reference pictures of a dinosaur from the top, side, and front, and inserted those into the 3D model. Then when I was designing the rest of it, I was able to use these pictures as reference for where all the joints should go and how big the dinosaur should be overall. I actually learned this trick when I was learning 3D modeling all the way back when I built my animatronic tiki bird head. Once I had the reference pictures in, I worked from the bottom up. So I started with the base and the legs. For the legs, I wanted him to have a staggered stance with one leg in front of the other. So I designed the legs in a sketch on top of the reference image and then used those dimensions and angles to make real-world parts that I could manufacture. Moving up, I designed the tail to be pulley actuated. The pulley attached to this servo pulls on a string that runs all the way down both sides of the tail. So when the pulley spins in one direction, it pulls the string on one side and releases string onto the other side. The tail responds by rotating and pivoting as if it was wagging. Moving up the kinematics chain of this robot is the body tilt. The actual joint is provided by a reducing T-joint. This T-joint runs on 3D printed bushings that allow really smooth movement with no worry about the pretty minuscule load of the rest of the animatronic. The servo that drives this joint is actually within the body of the animatronic. The servo is connected by a 4-bar linkage to the legs. When the servo outputs a torque, that force is transmitted through the 4-bar linkage and pivots the whole body. This 4-bar linkage mechanism is really important because it takes the stress off the bearings within the servo and it only needs to transmit torque. The actual stress and weight of the robot sits on that reducing T-joint. The neck tilt is a very similar story to the body tilt. I actually mostly reused the same 3D design. And lastly, in the head, I have 2 degrees of freedom driven by small 9-gram RC servos. One is a head tilt, so the whole head can tilt up and down. And then the very last movement that this animatronic has is a jaw open and close, which is driven by the very final servo at the tip of his nose. I started by buying or printing out all the parts I'm going to need for this animatronic. I did try to use as many off-the-shelf parts as possible for this design. It's a lot cheaper and faster to go to Home Depot and pick up a part than it is to custom design and 3D print at home. But even still, you can see I ended up 3D printing a lot of parts. The materials I did pick up from Home Depot were mostly PVC pipe and PVC fittings. I found that PVC pipes and fittings make a really fast prototyping material. It's super easy to cut, and then assembly is just pushing it all together. I first used PVC when I was prototyping my animatronic werewolf, and I found it's been super helpful in all my projects since. Just like how I designed it from the base up, I'm going to build it from the base up as well. Here you can see me cutting out the pipe to make the rectangular base that the animatronic stands on. Eventually I'll paint it black so that it's not very visible in the exposed show lighting. Next up, I'm assembling the legs. These are almost entirely made of off-the-shelf parts, but there are a few 3D printed parts that you can see, the bright orange ones. These are for the feet and the knees. I had to custom 3D print these because they're such specific angles to make the legs stand how I want them to. They had to be custom designed. You can't pick up a 112-degree fitting from Home Depot, so I had to make one myself. After the legs, I worked on the pivots that control the body and neck. Each of these pivots are made by a reducing T-joint like I mentioned during the design phase. You can see a little better here how the T-joint glides on these bushings, and that creates a much smoother movement. I had to cut a lot of the T-joint off to make it narrow enough to fit within the dinosaur body. Unfortunately, I did not account for the end stops within the T-joints. You see how these are meant to be used with pipes running water or another liquid. You're not supposed to push the pipe all the way through because that would block the other entrances. So they add these end joints to prevent you from pushing it too far in. Unfortunately, I didn't account for this when I was designing the bushings, so it didn't all fit together. Luckily, that's nothing a little bit of Dremel action can't get done. So I quickly sanded off that end stop, and then the joint was gliding smoothly on the 3D printed bushings. Then I connected the tail to the animatronic. The mount for the tail is actually also the bushings for the body tilt. That's why I had to prepare the joints before I could attach the tail. With the tail attached, I was able to play with the first degree of freedom of this animatronic. By manually pulling on the strings that are going to be attached to the pulley, I was able to see how this tail is going to wag. It looks alright, but I'm a little bit worried that once I get the foam and skin on, it's not going to bend believably. Next up, I assembled the body tilt and the neck tilt servos. It's really pretty simple. All I was doing was building an extension to the servo horns that come with these servos already. I need those to make the 4-bar linkages that drive these joints. The servos themselves attach to the torso through a bracket I designed and 3D printed. Next up was the head. The design of the head was pretty hard because it's a lot of actuation in a small space, but the actual assembly was very easy. I had already pressed in the aluminum rods that act as the pivots, so all I had to do was attach the servos and the linkages that actually control the motion. In the end, I did actually have to turn the jaw actuation servo around from how you see it now. The geometry of how that 4-bar linkage was set up meant that it was getting stuck at a certain point within its actuation range. This was stalling the motor and overheating it, which is not good. And then the last steps of building this animatronic was to attach the head to the neck, and then the neck to the body. At this point, the movement was looking pretty good, so I went about wiring the animatronic. I started by shortening the existing servo wires with zip ties, just so it's a little easier to maintain once the whole skin is on and it's a lot harder to access. Next up, I measured 2 lengths of 5-conductor wire. Within these wires, 2 of the conductors are dedicated to power, and the other 3 are dedicated to servo signals. One of these wires runs to the body to control the neck, body tilt, and tail servos. The other wire runs all the way up to the head to control the head tilt and the jaw. With those cut out, I crimped and soldered dew-point connectors on to connect to the servos with their standard servo connector. Finally, I zip-tied the wires along the dinosaur's body to keep the cable management neat and tidy, especially once the skin goes on top. Right now, I have the servos being controlled by a Raspberry Pi Pico, but I actually have some really exciting control circuitry coming in the mail that I can't wait to show you in the next part. The final step in assembly is a full test of the animatronic. So I programmed the Raspberry Pi Pico to cycle every servo through its full range of motion, and here it is. Here's the jaw moving, the head tilting, the neck tilting, the whole body tilting, and then the tail wagging. There are some improvements that I'm seeing now that the animatronic's fully built. I'm worried that the pulley-driven tail isn't going to hold up. It seemed okay in CAD, but now that I'm actually holding it, it doesn't have precise motion, and any slippage on the wires that run down the tail is going to cause the whole mechanism to fail. I'm especially worried about the slippage because I put the tensioners at the tip of the tail, which is basically going to be the hardest part to reach in the entire animatronic once the skin is on. To fix this, I actually think a chain of 4-bar linkages all the way down the tail would be the best solution. The other issue I'm seeing is that the 4-bar linkages that drive the body and the neck aren't exactly centered. Because all the force of the servos is transmitted through the linkages, there's a really big torque being imparted on the body. This is causing the whole thing to tilt to one direction. One way I could have fixed this is to use a servo with a dual output shaft. With a dual axle servo, I could put a linkage on either side of the torso. That way, the torque generated by either of the linkages would cancel each other out, so the dinosaur wouldn't bend in any direction. We've talked about the design and construction of this animatronic dinosaur, and we've even talked about some improvements I want to make. Be sure to subscribe and look out for the next video in this series, where we're going to be putting the full skin on this dinosaur and programming it.